As we saw last week, when an acid is added to water, some portion of the acid molecules give up a hydrogen ion to water to produce its conjugate base and a hydronium ion. When water breaks apart a chemical bond in another molecule, as it does in aqueous acid-base chemistry, that's called hydrolysis. We already saw hydrolysis in the organic section when we used water to reverse condensation polymerizations. In the case of Bronsted-Lowrey acids in particular, deprotonation by water also creates a set of positive and negative ions, so you'll also see hydrolysis referred to as ionization. One question we might ask is what fraction of the acid is deprotonated by the water at equilibrium? The equilibrium constant tells us about the relative strength of acids, but that doesn't quite answer the same question. Instead, we would want to compare the concentration of hydronium at equilibrium to the initial concentration of the acid. This can be represented as a decimal figure, but it's often written as a percentage and called the percent hydrolyzation, or sometimes the degree of ionization. For example, acetic acid has a Ka of 1.76 times 10 to the negative 5. If we make a 0.1 molar solution, we can calculate the concentration of hydronium at equilibrium according to acetic acid plus water is in equilibrium with acetate and hydronium. To calculate the deprotonation, we can use an ice table. Because our equilibrium expression is 1.76 times 10 to the negative 5 equals x squared over 0.1 minus x, where x is the concentration of hydronium or acetate, we can use a quadratic formula to find the solution for x is 1.32 times 10 to the negative 3 molar in this case as the concentration of hydronium, and that means we have a pH of 2.88. So now that we have the concentration of hydronium at equilibrium, we can calculate what percentage of the starting acid was hydrolyzed by water. That's 1.32 times 10 to the negative 3 divided by the concentration of the starting acid, 0.1 molar, times 100% gives us 1.32%. So unlike the equilibrium constant, the degree of ionization is not constant. Look what happens if we dilute the solution by 10 without adding any more acid. Now we would have 1.32 times 10 to the negative 4 squared divided by 0.01, so that's the reduced concentration of the starting acid, minus the amount that was taken away by the acid, so 1.32 times 10 to the negative 4. This equals 1.76 times 10 to the negative 6. That's our reaction quotient, and it's smaller than the K value. So that means that we're going to push towards more products being formed. And we can prove that again with an ice table. So now we have our new starting amounts of acid and acetate and hydronium. We're still going to change it by X amount. And when we find the value for X, it's 2.789 times 10 to the negative 4. And that means that our final concentration of hydronium is 1.32 times 10 to the negative 4 plus 2.789 times 10 to the negative 4, which is 4.11 times 10 to the negative 4, and our pH rises to 3.37, which should make sense. If we kept adding more and more and more water without adding any more acid, then the concentration of the acid is going to go towards zero, and the solution is going to behave more and more like neutral water, so its pH will move towards 7. Let's see what happened to the degree of ionization. So now we have 4.11 times 10 to the negative 4 divided by 0.01 times 100% is 4.11%. So even though the concentration of the acid is dropped, the percent of the starting acid that was hydrolyzed has just about tripled. This is a demonstration of Le Chatelier's principle. By adding water, we're adding more of one of the reactants, so we push the reaction towards the products in order to maintain equilibrium. If we continue the trend by diluting by another 10 times, we find that that degree of ionization is 12.42%. And if we really push it with another 1,000 times dilution, that means that the concentration of hydronium is only 9.492 times 10 to the negative 7 molar. pH is now 6.022, but the degree of ionization is now 94.92%. Almost 95% of the acetic acid has now lost its proton and been turned into its conjugate base, acetate. You can keep trying it if you like, and you'll see that the trend continues. The pH keeps moving towards 7, and the degree of ionization will keep working towards 100%. Earlier, we defined strong acids and bases as those that dissociate completely. But now that we've found a way to drive weak acids and bases towards 100% dissociation, we need a new way to differentiate between strong and weak acids and bases. Strong acids show a high dissociation even at high concentrations. And so for that to be true, they need to have a dissociation constant, Ka, that's much larger than 1. Where, as we've seen, most weak acids have a Ka, or acid dissociation constant, that's much less than 1. So we can still work with the assumption that strong acids are 100% hydrolyzed, but now with the knowledge that that's not really a defining characteristic so much as a convenient one. We'll talk more about what happens when we mix strong and weak acids and bases in the same solution in our next video.